Hi, this is example number 4 of section 1 till 3 of chapter 14, right? So we have here a 4 kilograms coil C right here that has a velocity at A. So the coil initially is at point 8. We can imagine right here. So the spring will be like here, and it has a velocity of 2 meters per second. And the spring has a constant of 400 newtons over meter and has an unstretched length of 0.2. So L0 is equal to 0.2 meters. And we are asked to find the velocity at B. So we have to imagine that this coil goes all the way to here, goes through C, and end up in D. So that's the final position. So this is position number A and position number B. And this is a semicircular rod of radius 0.4 meters. To find the solution, we will use the principle of work and energy. And we have to see that they don't tell us anything about the friction. So this is a smooth surface or smooth coil. So it doesn't generate any friction. So when we write our principle of work and energy, we know that the work of non-conservative forces is all the energy in position, the final position that in this case is P. So it will be a kinetic energy plus potential energy minus kinetic energy plus potential energy in the initial position. Since we do not have any work, since we don't have any work of non-conservative forces, we can talk about conservation of energy. All along the path. So we can say that Tv plus Vb is equals to Ta plus Va. So the kinetic energy plus the potential energy will be equals to the kinetic energy plus the potential energy in both positions. So let's calculate each of these values. So we know that the kinetic energy at A is equals to 1/2 mass velocity A squared. And we are given the mass, and we are given the velocity. So that is an easy, which 4 times the velocity, which is 2 meters, 2 square. Now, the potential energy at A. So the potential energy will be, we have the gravity, and we have the spring. So we can divide that potential energy in the gravity, let's call it Vg, and the spring, Vs. So to calculate the potential energy due to the gravity, we have to put a reference in our system, because we know that the potential energy done by the weight is the difference between the initial position and the final position. So I'm going to start and put here a datum. So I start here, and what I will have between A and B is a loss of potential energy. So right here, I have no potential energy, so due to gravity. So here I can say that this is 0, and then I have only the potential energy done by the spring. And the potential energy done by the spring, you know that is 1/2 K times delta L. Delta L means the difference between the longitude, the stretch, or how much stretch or compressed is the spring at that position, refer to the initial length of the spring. So here we have this distance, and they tell us that this is 0.1, and the unstretched length is 0.2. Therefore, the spring is compressed 0.1. So we can say that this is 1/2 K, which is 400 newtons over meters, times, I'm going to write 0.1 minus 0.2. And this is square. So this will be a negative value, but since it's square, the potential energy of the spring will always give us a positive value. So So those are those two. Now I will calculate the potential and energy in B and the kinetic energy in B. The kinetic energy in B will be 1/2 mass velocity V squared. That's the value I want to find. That's the value I do not have. So that will be 1/2 for velocity V squared. And finally, I have the potential energy in B, which will be, as we did for case 1, it will be the potential energy for the gravity plus the potential energy by the spring. The potential energy by the gravity, in this case, we do have potential energy because we will use the same reference frame or the line that we put for point A. So we do have a drop in potential energy done by weight. So that will be negative mgh. This is my potential energy done by gravity plus 1/2 k delta L squared. And this delta L will be different from that one, right? This is at A and this is at B. So this will be equals to negative, the mass is 4, the gravity is 9.81, and the height that it goes from A to B, this circular rod has 0.4 meters radius, so I drop 0.4. And the potential energy will be 1/2 k, which is 400 meters, and the distance. This is important to find that distance. How long, how stretched is that spring? As we see, this is 0.4, and this is totally 0.4, so this is 0.3, right? So to measure the same radius for the whole rod. So this, if this is 0.4 and this is 0.3, we have a triangle, right? 0.4, 0.3, and this distance, well, you can calculate that is 0.5, right? This is a 4-3-5 triangle. So the stretched length of the spring is 0.5, but we have to subtract the unstretched length, which is 0.2. So we will write right here 0.5 minus 0.2 squared. That gives us a positive value, but it's square, so it doesn't matter. So at the end, we will plug all these numbers right there. We can simplify so those values, but in any case, we have here, let me simplify those values right here. So here we have these 2 goes with 1, 2, so here I have 8, and here this is 200, right? So there will be 200 times 0.1 square. Here I have 2 velocity v square. Here I have 200 and so forth. So at the end, if I plug all these values right here in this equation, I will have dv, which is 2 velocity v square, plus the potential energy, which is right here, which is, this is a negative 4. I can multiply those after, right? Plus 200, 0.3 square, right? So this is kinetic energy B, potential energy B equals kinetic energy in A plus potential energy in A. So as you see, the only unknown is the velocity in B, so I solve for velocity B and I get the result, and the result is 1.96 meters over second.